Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today, we're going to look at forces on an incline. And to help us do that, we're going to use Taylor Swift for our example. So we got a 56 kilogram Taylor Swift is snowboarding down a 30-degree mountain on her iced skis. Should be an iced snowboard. What is her acceleration? So before we do this, let's look at an example if she were on a horizontal surface. And she's going to be a box for this sake. So we have a box sitting on a table, or Taylor Swift sitting on a table. And we're going to say something is pushing her forward. So we've got a force of a push. And we have friction going backwards. We'll call that FF. And there's two forces on the table itself. FG is down, and the normal force is pushing up. So we have the net force in two directions. We've got the net force in the X direction, and the net force in the Y direction. We have to separate these two when analyzing it. Now, what would happen to these forces if we put them on an angle? So let's look at that. So we're going to take our picture, see what it looks like, and rotate it 45 degrees. Notice, we still have the normal force going perpendicular to the surface. In this case, we have force of gravity going perpendicular to the surface, but in the opposite direction. We'll get to that in a second. We're going to call it something else. And we have the force of the push going down. And we also have the force of friction. Now, to make our lives easier, when we look at forces at an angle, we're also going to rotate our XY coordinates. So the normal force is going to be the Y coordinate. Sorry, that's a pretty crappy Y. And the friction force is going to be the X coordinate. So we're just going to rotate it along our coordinate plane. Alright, so let's look at Taylor Swift on her mountain. So we got our mountain. We'll draw a triangle for it. And Taylor Swift is skiing / snowboarding. Depends on how you interpret it. And she's going down the mountain at an angle 30 degrees. So let's label our forces for this. Straight down, we have the force of gravity. Perpendicular to the surface, we have the normal force, F sub n. And she's going against friction, so backwards, parallel to the surface, is FF. Now notice the force of gravity and the normal force are at an angle. So what we want to do is create component vectors. So we'll have, let me get a different color, going perpendicular to the surface but in the opposite direction. That's going to be gravity in the Y direction. So we'll call it FGY. And then, going parallel but the opposite direction of friction, we're going to call that FGX. If we were to rotate our triangle, this 30 degrees right here would appear right here, 30 degrees. Okay, so when analyzing forces on an incline, just like projectile motion, we want to look at the vertical axis first. So we'll do the net force in the Y direction. So we've got A equals F net over M. Always start with that formula first. Then we look at the forces in the Y direction. Well, here's our Y axis. Just for completion, here's our x-axis. So on the y-axis, we've got FGY and FN. So our net force in the y direction, A equals, FN is going up, so it's positive, minus FGY all over M. And our goal is going to be solve for the normal force. So let's multiply both sides by M. MA is equal to Fn minus FGY. Taylor-Swift, notice, is going down the mountain in the x direction. So our acceleration in the y direction is 0. So MA is 0. Now we could add FGY to the other side. That leaves us with Fn is equal to FGY. And FGY is our component vector. So let's look at our reference table really quick, because something's going to be slightly different. The last page on your reference table says that AX is A cosine theta and AY is A sine theta. However, notice our triangle here, if we use right triangle trig, opposite of theta is our x, and adjacent to the theta is our y. So in this case, our y is going to be attached to the cosine of theta. So we've got Fn is equal to Fg cosine theta. And the formula for Fg is Mg. So Fn is equal to Mg cosine theta. And we're going to stop with that right there. Looks like a lot of work, but notice you're just looking at the forces in the y direction right now. And then we're just simplifying from there. So now let's look at the x direction. What forces are acting on Taylor-Swift in the x direction? Well, we've got FGX going in the positive x direction and FF going in the negative x direction. So our net force, A equals F net over M, is going to be FGX minus FF. All over M. And we're solving for acceleration in the x direction, and it's already by itself. A equals, again, FGX is opposite the angle, so it's going to be FG sine of theta minus the formula for FF is mu Fn all over M. Okay, now here's where the magic happens. Notice right here, Fn is Mg cosine theta, and we have an Fn right here. So we could plug Mg cosine theta into there, and we'll also simplify Fg into Mg. So we've got A equals Mg sine of theta minus mu Mg cosine of theta. This is where algebra comes in handy before plugging in our values, all over M. Now we got our M on the top, M on the top, M on the bottom, so our M's cancel out. And we're finally left with the acceleration is equal to G sine of theta minus mu G cosine of theta. And that's it. So let's look up what our mu is. If we go back to Taylor-Swift, she is on, should be waxed skis, not ice skis, sorry. Wax skis on snow. So she's snowboarding, wax skis on snow. Sorry about that. So let's look at our reference table. If I could pull it up. You could do it. Okay, reference table, sorry. On the front page, we look at approximate coefficients of friction. Since she's moving, it's going to be wax skis on snow. So the coefficient of friction is 0.05. So now we just plug and chug. Acceleration is equal to 9.81 meters per second squared times the sine of 30 degrees minus 0.05. Notice mu does not have units. It's one of the two values that do not have units. Times 9.81 meters per second squared times the cosine of 30 degrees. And we do some plug and chug, and we get the acceleration is equal to 4.48 meters per second squared. So, brief summary. Draw your picture on the right triangle. Label your forces. In the y direction, we have Fn and Fgy. In the x direction, we have Ff and Fgx. So that's step 1. Step 2, solve for the normal force in the y direction using A equals F net over m. Step 3, solve for the acceleration in the x direction, also A equals F net over m, and plug and chug. Well, that's it for me tonight. Hope you're able to follow along. Until next time, see ya.